Dear student, this is my third lecture on the elastic property of the materials, and in this chapter, let us suppose this is the filaments. So these are the parallel filaments. So these filaments have been placed one over the others in a parallel way, which is going to constitute a beam. So this is just like a beam which has been constituted from this. Okay, so as you can see, so this is a beam, right? So this beam has been made by the different filaments. So these are the different filaments that have been taken over here. So what you can do, you can just imagine a scale. So we have taken a meter scale, which you are using in the physics lab. So we have taken a meter scale, and on the meter scale you have the top layer and then you have the bottom layer. That meter scale is being bent. So this is the meter scale which is being bent over here. So here you can see, so here we are bending this meter scale, so like this. So all its layer is bending. So one by one all the layer is bending, as you can see in this diagram. So now you locate here the different layers. So this is the top layer and this is the bottommost layer. So we have the different layers, top layer and bottom layer. Now you locate in this, you will find that the top layer of this is getting elongated if you are going to apply the force, and bottommost layer is getting contracted. All right. So therefore the contraction, what we can say, the contraction is, that is elongation is increasing as we are moving from the lowest surface to the topmost surface. So as we are moving, this is going to increase. All right. So from here to here, the elongation slowly is increasing. So at the therefore, what we can say, at the topmost level, the elongation will be maximum, and at the bottom level, the elongation will be minimum. Therefore, what we can say, as we are moving from the top to bottom, like this. So this is how we are moving. So what is happening? Elongation is slowly decreasing, and therefore we will be getting in between one layers where there is neither elongation nor contraction. Because what is happening after this, instead of the elongation, we will have the contraction, and the lowest most surface has got highest contraction. So the contraction, so what we are saying here, we are getting one particular layer. So you can look at this layer. You see this layer properly. This layer, there is neither the elongation nor contraction. And this layer where there is no elongation or contraction. So again, I am representing this with the yellow line. This will be called as the neutral axis. So what is the neutral axis? What is the neutral axis? If you are going to bend the scale, so in between there is a layer where there is neither the extension or the elongation nor there is contraction, and that axis will be called as neutral axis. So let us see this is what has been represented. So what is the beam? Beam is defined as a rod or circular or rectangular. Here we have taken rectangular bar of a uniform cross section whose length is very large than its breadth and thickness. So its width, that is the length, is going to be larger than its breadth and thickness, and dimension, of course, the length must be very, very large compared to its breadth and thickness. All right, let's continue. The characteristic of the beam. The beam may be considered to be made of the large number of the thin plane horizontal layers placed one over the others. Each layer in turn consists of a number of the thin parallel longitudinal metallic fiber or filament. So what we are saying, it can be the fiber or filament arranged side by side as I have represented in this diagram. So this scale has been made with the parallel lines from this. So these are the parallel lines. So this is how what has been placed over here there. So this constitutes your beam. So what I define, when a straight beam is bent, as I explain you that what we are going to do, we are going to bend this. So when this is going to be bent, the outer layer get elongated and lower layer get contracted, but one layer between them is neither getting elongated nor it is getting contracted, and that layer, as I define you, is called neutral axis. So here this will be your neutral axis. This axis is called neutral axis, which is neither going to be elongated nor it is going to be contracted. Okay, fine. So what is the neutral axis? The neutral axis is the axis in the cross section of the beam or shaft along which there is no longitudinal stress or strain. So because there is no contraction or elongation, so no stress or strain is acting on this. Okay, let's move further. The elongation or contraction of any layer is proportional to the distance. So as I told you, as you are moving from here to upper surface, from the neutral axis you are moving to the upper surface, the elongation is increasing. And similarly, if you are moving down, so what is happening? Contraction is increasing, right? So as you are going up, let us suppose we are going x1, x2, x3, x4, and here we have come to the x4. This is the x4 we have come. So here the elongation will be maximum. Similarly here the contraction will be maximum. All right. So what we are saying, the elongation or contraction of any layer is proportional to its distance from the neutral surface. Hence outer layer are maximum elongated or contracted. So outer layer does mean any that is the top surface or the bottom surface. It is getting maximum elongated or contracted. All right. So that makes you the beam. Now we are going to find out what is the bending moment. So bending moment is defined as the total moment of the force acting on upper and lower surface of the beam. So you have seen the beams. So therefore, if you are going to bend the beam, so some force is acting on the upper surface, some force is acting on the lower surface. So the total force which is acting on the beam is called the bending moment, right? So I can just give you an example. What do? You take a meter scale, hold in your hand properly, stiffly, and let us suppose say your meter scale, and on other hand or other side you put the load. Slowly you go on increasing the load. What you will find? You will find some stress on your finger, and if you are not able to hold it properly, you will not be able to hold your scale. The scale will come out from your hand. So what is happening? That is because of your bending moment, a force which is acting. So what we are going to calculate over here? We are going to calculate the expression for bending moment. So this is the expression. For this expression of the bending moment we are going to calculate in this lecture. All right. So what we have done is the same scale we have taken. So this is your A, B, this is your topmost layer. And again we have C and D. This is your bottommost layer. Naturally this is your in between. EF is the in between is the layer. So this is your neutral axis, right? So this is what has been shown in this diagram. Now what we are going to do? So this one end of this is fixed. So this end has been kept fixed, just like you are holding the scale in your hand, and one part is fixed, another part you are putting the load. So here we are putting the load. This is the load that we are giving on this. All right. So therefore what is going to happen? Let us see if you are going to do this. So let's proceed further. So this, now what we have done, a small part of this beam has been taken. So what we have done here, P, B, G, F, Q, C. So this is what the small part of this has been taken. Of course load W is already there. Okay, so now let us see in this case what is happening. Now we have put the load. Under the load it has got bended and it is making a arc. So what is happening? It is making a arc. So if it is making a arc, so naturally it will have a radius of curvature. So this will call as the radius of curvature. Here I have taken from the top surface, right? So this is the radius of curvature. So what is happening? This surface has got bent. This is maximum bending is there. So because of this bending, it is creating a radius of curvature. Now I will give you a simple example. Let us suppose all of you use the plane mirror, and all of you know what is the radius of curvature in case of the plane mirror is infinite. Why it is infinite? Because it is completely plane. Now same mirror, if you are going to bend, then you will have the radius of curvature. It will have a numerical value of radius of curvature. So exactly in the similar way, so that mirror you call concave mirror or convex mirror, the way you are going to fold it. So exactly in the same way, here we are going to have a radius of curvature of the beam which we have bended. So let's proceed. What we can find over here. So the same cross-sectional area we are showing over here, all right, on which we have put a particular load. So consider the beam, that is A, B, C, D of the length. This is the length we have taken as L, and W is the load that we have given. Upper surface is getting elongated, and of course they will feel a force, and lower surface is also getting contracted, and because of that also you have a force. So lower portion DC get contracted and experience an outward force, whereas the neutral filament EF. So this is the interesting thing. This is the neutral filament. This is the neutral filament EF. In this neutral filament, there is no elongation or there is no contraction, and therefore no force will be acting on this. All right. The beam experiences two opposite couples. As a result of that, the beam will come in rest. So if you are going to put a load on this, after a particular certain interval of the time, the beam will come to the rest. Okay, let's put. Now again, as I explained you, the small part, a small part of this has been taken. Now from here, that is from the neutral axis, this is the neutral axis that we have taken. From the neutral axis, we have taken the arc. This is the arc that we have taken, right, that we are calling radius of curvature. So this radius of curvature has been taken from the neutral axis. This we are calling as R. So this 2 arc, that is 2 radius, is making a particular angle over here, and let us suppose that angle we are calling as theta. So naturally, if the theta is very small, theta is equal to angle is equal to arc upon radius. So theta equal to what we can write? GF upon GO or R. GF upon R. So this is here we say there is no bending. Now what we are going to do? From here we are moving a particular distance R, and we have come to the top surface PB. So now this arc is going to make the total radius is equal to how much? R plus capital R. This is your R, and this value will be your small r. This value will be your small r. So the total value you are getting is capital R plus small r, and with respect to this we are going to do the calculation. So as we have already seen, the bending moment of a beam is equal to the restoring couples acting on the beam, because of which it is coming in the rest. So this is what I have told you there. So we have taken a small cross section of this, and this is what is being written. GF is your neutral surface, and with respect to that we are going to do the calculation. So O is the point. So this is your radius of curvature. All right. So let's move further. All right, same cross section has been shown again over here. So now this is what we are saying. The GF, this is the arc. This is your arc. GF is your arc. So what will this value of GF is equal to R into theta, as theta is equal to arc upon radius. So GF is equal to how much? GF equal to R into theta, where angle, this is the angle theta, which it has been made by this. Now let us see. Let's calculate what is the angle made by PB, outermost layer. So naturally this PB is also making the same angle theta. So if I calculate what is the length of this arc PB in terms of this R and this capital R plus a small r. So what we can say, this is equal to capital R, this capital R plus a small r. This is your total length of the arc, right? So this topmost layer, what we can say, this topmost layer is equal to PB. This is your PB. This is nothing. This we have taken as PB. So this PB is equal to R plus small r into theta. All right. So what we can say, naturally this GF is without any bending, and PB is with the bending. If I am going to subtract with this, then what we will getting? We'll getting what is the change in the length, and therefore we will able to find out what is the strain on this. So what will this strain? So linear strain, as we know, is equal to increase in the length upon initial length. So what is the increase in the length? So increased length is equal to, this is your increased length. This is your increased length. So this is your r plus r into theta here. R plus r into theta. And r theta for this you have got r theta. This is your neutral axis, right? So we have subtracted r theta. So how much we are getting? Just you do the simple calculation. So linear strain we are getting is equal to small r upon capital R. This is your simply a linear strain. Okay, so let's proceed further. Now let's calculate what will be Young's modulus. So Young's modulus is equal to stress upon strain. Okay, so from here linear stress, here just do the cross multiplication. Linear stress equal to y, this y into linear strain, into this linear strain. So y, this is your Young's modulus equal to your this y, and linear strain you have calculated over here. This is the linear strain that you have calculated, r upon small r. So that value we have substituted over here. Now from here let's calculate what will be the force. So stress is equal to force per unit area. Stress is equal to force per unit area. So if I am going to multiply this strain by cross sectional area, sorry, this stress by the cross sectional area, then we will be getting the force. So what will be the force? Linear stress into cross sectional area, because what is the stress? Force per unit area. All right, so this is what we have taken. This is your y, r upon r. This is your stress into cross sectional area. We have taken A is the cross sectional area of this beam, so we have multiplied by this A with this A. Now let's calculate what is the moment of the force. So what will the moment of the force? Moment of the force is called force into perpendicular distance. So moment of the force is your force into perpendicular distance. So what is the force we have calculated? This is the value of the force that we have calculated. This is the value of the force that we have calculated. Multiply this with the perpendicular distance. What is the perpendicular distance? This is small r. So what we are getting? We have multiplied this by small r here. So we are getting capital R A into r squared. This is your moment of force. Okay. So the total moment of the force acting on the upper and lower surface. So now this is the moment of the force acting on a small cross sectional area. So what is the total moment of the force acting because of both the lower and upper surface? So this is what we have to calculate. So what we can do? If you are going to take the summation of this, that is just or you can say we are going to take the integral of this value, then we can find out what is the total value, right? So we can do the integration of this. So let us see, this is what we have done in the next slide. So the bending moment of the force is equal to total moment of the force acting from the upper and lower surface of the beam, because the force is acting both on the upper surface and the lower surface. So what we have done, we are going to just do the summation of that. So y upon r is your constant, we have taken out of that, summation ar square, and this sum of ar square is called geometrical moment of inertia. This is called, here I have not written moment of inertia, this is called geometrical moment of inertia, and we are representing this by Ig. So what we can say, this value is coming out equal to some y upon r summation ar square. So ar square equal to how much? Aig. So the total value, what we can say, this is the bending moment. So bending moment of the beam will equal to y upon r into Ig. So this is the bending